Welcome to the world of distributed coordination. In this presentation, we will explore essential mechanisms for maintaining order and consistency in distributed systems. Distributed systems are complex, and keeping everything running smoothly requires careful coordination. We will cover key topics, including clock synchronization and mutual exclusion. Let's dive into clock synchronization and the challenges it presents. In a distributed system, each node has its own clock. However, these physical clocks often drift at different rates due to various factors. Network delays are variable and unpredictable, making it difficult to accurately synchronize clocks across different nodes. Message transmission times are not constant, adding to the complexity. Process scheduling affects timing precision, and hardware variations can impact clock accuracy. As you can see in the illustration, Node A's clock shows 10 o'clock, Node B's clock shows 10 minutes past 10, and Node C's clock shows 2 minutes to 10. This illustrates the phenomenon of time drift across different nodes in a distributed system. Now let's explore some clock synchronization algorithms. First up is Cristian's algorithm, a centralized approach where clients synchronize with a time server. The client requests the time from a central time server and accounts for network latency by measuring the round-trip time. This algorithm assumes symmetric network delays. Here is how it works. T1 is the local time at which the request is sent. The server time is obtained by requesting time from the server. T2 is the local time at which the response is received. The round-trip time, or RTT, is calculated as T2 minus T1. The adjusted time is then determined as the server time plus half of the RTT. Next, we have the Berkeley Algorithm, a decentralized approach where nodes average their clock values. A coordinator polls all machines for their time and calculates the average time from all responses. It then sends adjustment values to each machine and is fault-tolerant against individual clock failures. In the Berkeley algorithm, the coordinator collects times from all nodes, removes any outliers, and calculates the average time. Then, for each node, it sends an adjustment value, which is the difference between the average time and the node's time. Let's examine the Network Time Protocol, or NTP. NTP is the most widely used protocol for clock synchronization on the Internet, designed to resist the effects of variable network latency. It uses a hierarchical architecture with stratums or tiers, and utilizes UDP port 123 for time synchronization. It achieves sub-millisecond accuracy on local area networks, and tens of milliseconds on wide area networks. It employs sophisticated algorithms to filter outliers and jitter, includes security measures against spoofing attacks, and continuously adjusts the local clock rate to match reference clocks. Here's an overview of the NTP hierarchy. At the top, we have Stratum 0, which includes atomic clocks. Stratum 1 consists of primary servers, which are directly connected to Stratum 0. Stratum 2 comprises secondary servers, which synchronize with Stratum 1 servers. Finally, Stratum 3 includes client machines that synchronize with Stratum 2 servers. Now let's discuss logical clocks in distributed systems. Lamport's logical clocks establish a partial ordering of events without relying on physical time. It captures causal relationships between events, and each process maintains its own logical counter. The counter increments on local events, and messages carry the timestamp of the sender. The receiver updates its clock to the maximum of its local time, and the received timestamp, +1. Here are the Lamport's clock rules. Rule 1 states that before an event occurs at process P sub I, the logical clock at I is increment. Rule 2 says that when process P sub I sends message M, M's timestamp is set to the logical clock at I. Rule 3 says that when process P sub I receives message M, the logical clock at I is updated to the maximum of the logical clock at I and M's timestamp, +1. In this example, events are labeled with their Lamport timestamps. When a process sends a message, the receiver updates its logical clock to be greater than both its current value and the timestamp in the message. Process P1 has events with timestamps 1, 3, and 7. Process P2 has events with timestamps 2, 5, and 8. Process P3 has events with timestamps 4, 6, and 9. There are also messages sent between P1 and P2, P2 and P3, and P3 and P1. Let's move beyond Lamport clocks and explore vector clocks. Vector clocks extend Lamport clocks to capture the complete causal history and detect concurrent events in distributed systems. Each process maintains a vector of counters, one per process. Process P sub I increments only its own counter in the vector clock, and messages carry the entire vector timestamp. On message receipt, vectors are merged by taking the maximum of each element. Here are the vector clock rules. Rule 1. Before an event at process P sub I, its own counter in the vector clock is increment. Rule 2. When process P sub I sends message M, M's vector is set to the current vector clock. Rule 3. When process P sub I receives message M, for each element from 1 to n, the vector clock at I is updated to the maximum of its current value and the corresponding element in M's vector. Then the process increments its own counter. In the example timeline, each event is labeled with its vector clock value. The vector clock captures the dependencies between events across different processes, allowing us to determine causality and concurrency. Also, the comparison between Lamport and vector clocks are given. The Lamport clock gives partial ordering and captures the happen before relation. The vector clock captures concurrent events. Vector clocks requires order of n space as compared to order of 1 for Lamport clocks. Now let's tackle the challenge of distributed mutual exclusion. This involves ensuring that only one process at a time can access a shared resource in a distributed system without a central coordinator. This requires the following: no shared memory or common clock, communication only through message passing, unpredictable message delays, and processes that may fail independently. The requirements include safety, which means only one process can execute in the critical section at a time, liveness, which means requests eventually succeed without deadlock, and fairness, which means requests are granted in order of timestamps. Here are some common algorithms. Lamport's algorithm uses logical timestamps to establish a total ordering of requests, with each process maintaining a queue of timestamped requests. The ricart-agrawala algorithm optimizes Lamport's algorithm by reducing message complexity, where processes request permission directly from all others. Token-based algorithms involve a unique token circulating among processes, with only the process holding the token able to enter its critical section. Let's delve into how Lamport's mutual exclusion algorithm works. This algorithm uses logical timestamps to establish a total ordering of critical section requests in a distributed system. The steps are as follows. First, when a process wants to enter its critical section, it timestamps the request and sends it to all other processes. Second, when a process receives a request, it places it in its local queue ordered by timestamp. Third, the process sends an acknowledgement message to the requester. Fourth, a process can enter its critical section when its request is at the head of its queue, and it has received messages from all other processes with timestamps larger than its request. Fifth, after exiting the critical section, the process removes its request from the queue and sends a release message to all other processes. This requires 3 multiplied by n-1 messages per critical section entry and ensures total ordering of critical section requests. Here is the pseudocode implementation. When a process wants to enter the critical section, the clock is increment, a request timestamp is generated, and a request is sent to all other processes. It then waits for all replies and enters the critical section. When exiting, the release message is sent to all other processes. When a process receives a message, the clock is updated. If the message is a request, it is added to the request queue, and a reply is sent. If the message is a release, the request is removed from the queue. Finally, let's explore token-based mutual exclusion. In the token ring algorithm, processes are arranged in a logical ring, and a unique token circulates among them. Only the process holding the token can enter its critical section, and after execution, the process passes the token to its neighbor. This method requires no explicit request messages, and the token contains a queue of pending requests. Here's a comparison with other algorithms. Lamport requires 3 multiplied by n-1 messages per critical section, with the advantage of being fair but with a high message count. The ricart-agrawala algorithm requires 2 multiplied by n-1 messages per critical section, offering improved efficiency, but is vulnerable to failures. The token ring requires from 1 to n messages, providing low overhead but with potential token loss issues. As we can see, process P2 currently holds the token and is in its critical section. After completion, it will pass the token to P3. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.